Hello, my name is Athanasios Mastrogeorgiou, and I'm going to present you my work we have done the last months at the Legged Robot team of NTUA. Our focus is to create a training framework that produces efficient motions, efficient trotting gaits using deep reinforcement learning. Laelaps II is a quadruped built in-house at NTUA. Yes. So Laelaps II is a quadruped robot built in-house at NTUA. Its total mass is 40 kilograms and uses two electrical motors per leg, actuating the knee and the hip respectively. So let's go present the overview of the presentation. First, we are going to give you an insight on the detailed MuJoCo model that we have created. Then we are going to present the total trajectory planner, which is very critical part of the multi-layer control architecture that Laelaps is using. Then we will go to the training framework, the reward function, which is a crucial part of the whole process, since we included parts that we have included parts of electric losses, let's say, that differentiate us from literature. Then we will explain the observation space and the action space. We'll go to the results, the conclusions, and the steps forward. The actuation unit is designed and built in-house. The gearbox and the pulley have attributes that affect the energy consumption. The most significant ones are the drivetrain's friction models, which we have identified with great accuracy. As it is illustrated in the lower set of pictures, the behavior of the friction of the actuation units tends to be linear, so the model is presented here on the bottom. This model is ideal for model-based control designs in terms of execution time, while at the same time it exhibits a good R-squared index. All the electrical and mechanical properties of the model were derived from the components datasets and were experimentally verified. So we created a high-fidelity simulation. Concerning the total trajectory planner, Laelaps II uses a multi-layer control architecture. The low-level controller uses a dedicated PV controller, which is running on the microcontroller on its leg and performs trajectory tracking. The total trajectory is the one shown in the upper left corner. It's a semi-elliptical one, as you can see. The main parameters are the time needed for the swing phase, the time for the stance phase, and the A and B radii of the semi-elliptical trajectories. I have to mention that the toes touch the ground with zero angular velocity. This scheme reduces disturbances and produces a car-like motion for the robot. Concerning the reward function, that we started from the calculation of the total energy. This differentiates us from literature, since we included the mechanical power of the actuators and the electric losses. So the first term of the reward function is looks like the cost of transport. We have not included the gravity acceleration and the weight of the robot, since they are constant and they are included in the weight of this reward term. We have included an epsilon term in order to avoid division by zero, since, as it is easy to understand, the quadruped robot consumes energy even to stand still. So this could lead to division by zero. So we include this energy term. The other two terms of the reward function is more straightforward. The one promotes forward motion and penalizes drifting motions. So the sum of these three terms produces the reward function that we are using in our training. Concerning the actions and observations, the action space consists of the action space consists of the coordinates of the center and the A radius of the semi-elliptical trajectories for each one of the four legs: right front, right hint, left front, left hint. The horizontal radius A is directly coupled to the body's velocity and direction, thus to the kinetic energy. So it's very important to include it in the action space, since the agent learns to modify this radius in order to reduce the cost of transport. Concerning the observation space, it consists of linear and angular components of the body's velocity, along with its roll, pitch, yaw angles. We have chosen to include the history of the observations in our observation space because in our use case we have chosen a stride duration of 1 second and specifically 0.5 seconds for the stance phase and 0.5 seconds for the swing phase. And in order to track this motion well, we have included 10 times faster observations. We have included the history of the observations, which equals to 10 times faster tracking of this phenomenon. Concerning the training framework, as I mentioned in the previous slide, Laelaps is using a multi-layered controller. The agent produces the planner parameters to be applied in the next step. In turn, the low-level PP controller performs the trajectory tracking of the produced trajectory. So the simulation step and the agent step are different. Specifically, every 0.5 seconds, the agent chooses the next action to be applied. Then the simulation is running at 1 kilohertz and is tracking the newly created trajectory. So let's go to the results section. The difference between these two diagrams is that on the left is the produced motion without the reward term, and on the right is the reduced energy consumed during a transition to the goal of Laelaps II robot with a reward term. By penalizing electrical losses and the mechanical power, total energy consumption of Laelaps II is significantly reduced. Specifically, it is reduced by 37%. So another byproduct of our work is that by increasing efficiency, by applying this energy efficient term that I described before in the framework, smoother motions are produced. Bounded body angles, specifically bounded body angles, the quadruped is not diverging from its goal. It follows an almost straight line to the goal. And the second is that longer distance is covered since less corrective motions are needed. So on the same time, the robot travels longer distances, which has a significant impact on the cost of transport. Concerning, as far as the cost of transport is concerned, over the red, you can see the cost of transport if we don't use any energy efficient term in our training framework. Then with yellow, you can see a reward function from literature that it penalizes joint accelerations. With purple, reward function from literature that also penalizes the mechanical power. And with blue, our approach, which penalizes the mechanical power and the electrical losses. So compared to similar learning approaches, our approach achieves the lower cost of transport. And compared to the red one, which has no efficiency, it takes no efficiency in, does not consider efficiency, has 37% lower cost of transport. So another byproduct of our research is that we found out that using this efficiency approach, the produced footsteps tend to be within a specific area of the leg's workspace, which coincide with similar analytical approaches that in order to avoid antagonism between the actuators of the leg should move in specific areas of the leg's workspace. So our conclusions are that smoother motions are produced. We have reduced the cost of transport, and if you compare it with an approach without energy efficiency in mind, it is reduced by 37%. Fewer corrective actions were needed during the transition to the goal. This means that the robot body is moving in small ranges. The footsteps, which means that the ellipse centers and the AID produced by the proposed deep-RL scheme tended to be within a specific area of the leg's workspace, which coincides with analytical approaches that we have found in literature. Concerning the next steps, first we would like to apply the learned policies to Laelaps II robot utilizing a ROS package that we have created also in-house in the Control Systems Lab that interfaces high-level control with FRCAD network. We want to investigate how the gains of the low-level PV controller affect energy efficiency. We want to investigate how the observation space could be extended with terms that improve the quality of the motion, adapt the current framework to produce energy-efficient motion on rough terrain, and last, validate analytical approaches such as that we are which is also a research direction in our lab. And this is indicative references. The first one is the one I was mentioning at. And all of these are the basis of our research. The team involved in this project are my colleagues Aristotelis and Kostas, who are also here. And thank you for your attention.
Is there any question from the audience? Yes, I can borrow.
So interesting talk, but I'm not too sure what the kind of the final bottom line is. Is it to produce the most efficient trotting process, or to produce the to complete a particular task which involves trotting with minimum of total energy expenditure? You know, it trots from A to B to perform a task. So is that the final aim, to minimize the energy consumption in that process?
We want to minimize energy consumption, but we have chosen one use case, which is trotting, which is a common gait pattern that legged robots are using, specifically our robot in our lab. We have usually walks using the trotting gait, chooses the trotting gait. And it also is a good, it also goes with our multi-layer control architecture, which is a high-level controller and a low-level PV controller running on the microcontrollers at the robot's legs. So it's both for what you have asked. We want to minimize energy, but trotting is a use case that is very common in legged robots.
Yes, it's just, can you hear me?
Yes.
Yeah, it's just that when the talk opened, the first thing that came to my mind is that this just reminded me of the, you know, simply driving a car at the most efficient, energy efficient speed. But it's more than that, isn't it? What you're looking at? Yeah.
In fact, one of the research directions is that we want to find the areas in the workspace that of the workspace of the leg, in order to reduce antagonism between the actuation units on the leg itself, and we want to approach it from the deep reinforcement learning angle. We want to train the algorithm and see if the outcomes of the algorithm coincide with analytical approaches in the same research direction.
Okay.
Any more question? No. Can you indicate us which are the main factors that can affect or increase the energy efficiency of this robot?
Excuse me?
Which are the main factors from the environment that can increase the energy efficient when this robot will be applied in real application? For instance, the speed of motion or the environment, which environment factors can affect that?
There are many environment factors. That
Yes,
can
of course, the main ones.
The speed, for example, the speed of motion, which is connected with the stride length,
Yes.
affects the kinetic energy, so it affects the efficiency. But in general, also other research directions that I also include in my presentations are the gains of the PV controller. For example, how stiff the leg is, what forces it exerts to the ground. Sometimes you want it the legs to be more stiff because probably you want it to carry payload or things like this, or you want it to make it walk on sand or different terrains with different compliance. So,
and do you need to calibrate PID control for stance phase and swing phase? They are different, the gains, or not?
In our legged robot, we're using the same gains, but this is also one of we are actively researching. We're actively conducting research towards this direction. So it's an open question for us because we are somehow applying indirect impedance control. So how stiff or not stiff is the leg is an open question.
Okay, thank you.